Okay, so the last one we will do, these are hopefully helping you understand something about functional dependencies. By the way, this is also the basis of a lot of the AI that's being developed today that basically has to do with social choice and preference models and all of that has to do with this kind of simple way of processing implications. Okay, so let's try and figure out one more thing, which is the projection of functional dependencies. So the idea is that you have some set of functional dependencies, but you decided to decompose your relation. I want to find out what is the maximal set of dependencies that I can enforce given this new set. Why is that the case? Well, suppose you had this set, and then you had AB implies C, C implies D, and like this. And now I want to decompose this into two new sets. One is going to be R1 of A, B, and D. And the second one is R2 of B, C, and D. Okay. Well, actually, let's make this B and D, because I want to be bad. All right. So the point is that I want to know of these functional dependencies, which ones apply to A, B, and D, right? I can no longer have AB implies C, right? Because AB and C are not in the same relation anymore. But there are things that are implied by that only involve attributes A, B, and D, which are what? So what can I say about attributes A, B, and D? They are good attributes. Yes. AB implies D, yeah. So generally, lots of things are true, but this is non-trivial, right? AB implies D. What can I say about B and D? I don't think anything is true about B and D, right? So these are the functional dependencies that I can enforce because they are in the same relation. But some of them are lost, okay? So basically the idea is that I am taking this set and projecting into the attributes in here. So I am projecting F, projecting that into A, B, and D to find this set. And I'm going to project it to B and D to get this set. Okay? That is the best I can do if this is how you decide to decompose. Okay? So the projection is actually kind of an easy thing to define now that we know all the mechanics. So projection of F onto a relation R is found as follows. Okay, find all x implies y in F prime. Find everything that's in the closure that only involves attributes in R. Let's call this R1. Find all that only involves attributes in R1. Construct set F1. Then simplify F1 so that F1 is actually in minimal cover. If you don't like this exponential algorithm for finding the projection, I'll give you another exponential algorithm. So if you don't like this, what we can do is for all subset X of attributes in R1, find X plus in F. Okay. Then basically add to F1 X implies X plus intersection with attributes in R1. There's a lot of hand waving, but you understand where I'm going. So basically find the closure of everything in F1. Then of the things in closure, only choose the attributes that are in R1 already. And add a functional dependency like this. Then put F1 in minimal color. Okay. So if I were to apply the same exact, this algorithm to the simple example I had, so let's say I have R1 ABD, right? I will actually find the closure of A, closure of B, closure of D. Then I have to find the closure of AB, AD, and ABD, and A, B, and D. Okay. So now to find, for example, you will find closure of A is A, closure of B is B, closure of D is D. Closure of AB is AB, CD. Closure of AD is AD. Closure of BD is BD. And closure of AB and D is this. So that would imply that I have things like A implies A, B implies B, but those are all trivial, right? So these will all give me trivial functional dependencies. This is trivial, right? None of those are useful. What I do get is I get AB implies ABCD. So the AB part is trivial, but I have AB implies C and D, but the C is not in my relation, so I'm going to drop it to get AB implies D. And from this, I have ABD implies D, but this is also trivial, so I will get rid of that. So what I end up is AB implies D. And if you were to do the other one, you will find that there are no non-trivial functional dependencies. As a result, I'm going to have none. So for R2, B and D, so this is F1, and F2 is nothing, because there are no non-trivial functional dependencies. Okay? All right. So this is all the mechanics that we need to now actually talk about doing something good with all the stuff we've learned. Okay? Any questions so far? All right, so now let's try to do something useful. So, let's see. Okay. So we said that if a relation is not in BCNF or third normal form, we need to decompose it. So whenever we do decomposition, we basically are given some original relation. And a set of functional dependencies. And then you give me a proposition of what is a good decomposition. You say, well, I want to put A, B, C, and D here, and A, B, E, and F here. And you say, well, is this a good decomposition or not? Right? So obviously, that will depend on whether what the functional dependencies are. So we said that basically what we are going to do is first find F1 and F2 that are projection of R onto these. Okay. Then I'm going to check if things in F1 and F2 together still imply the same thing as that was originally. So then I will ask, is F1 union F2 equivalent to F? Okay. So if I take the union of these two, will it give me the same exact thing? If so, I will say that this is dependency preserving. Whatever was original dependencies, I can still enforce them in the resulting relations. And the beauty of this is that then whatever was incorrect according to the original relation will continue to be incorrect. So if you cannot have two actors with the same ID and the same name, if that functional dependency is preserved somehow, if not directly but indirectly, then that's good, because then I will not have randomly the same actor with the same ID but different names, right? So even though it may not be immediate, if through other functional dependencies that's still implied, I will not have bad data, right? So if so, then the composition is functional dependency preserving. Okay. Now you know how to check this. We learned how to check two things are the same. We learned how to find the projection, so we can do that. Okay. The second one is a little bit more subtle. The moment you decomposed, did you do something bad? Okay. So that means, if I computed R1 by projecting A, B, C, D from R, then computed R2 by projecting A, B, E, F from R. Then I took the natural join of these. Are these guaranteed to be always the same, no matter which database instance you have? Because there may be some database instances that they will give the same result. That's okay, but is it always guaranteed to give you the same result? Okay, that's the thing we care about. Is it always the case that you will never get something different when you join? By storing this information separately, you're not losing anything. So ultimately, what you want is both of these to be true anytime you do a decomposition. But we will see the cases where the first one is not necessarily true. If so, then two may also suffer, because over time they may result in being different. But first we care about is when I do this decomposition, it's actually the same or not. So to find that is the case, we are going to see an algorithm, which is also semi-deterministic. Well, it will always say the same yes and no, okay? So how to check if a decomposition is lossless? Okay. If you want to see an example, let me show you an example. And I will show you how I got this example exactly in a second. So let's say I have the case that I have A, B, and C, and that A implies B. Okay? And nobody implies C. So the key in this case is AC. Okay? Suppose now I have R1 that has A and C, and R2 has B and C. Okay? And here's an example. Okay? Suppose this is my relation. So if I were to decompose like you want, if that's really what you want, I will get AC and A2C. This is R1. And R2 I will get B1C and BC. Okay. So now, if I were to do the Cartesian product, the natural join, I will get a relation with A, B, and C, but my join is on which attribute? C, right? C is the common attribute. So I will get A, B1C, A, B, and C. Then I will get A2, B1, C, and A2, B, and C. Did I get the same result? No. In fact, I generated this using the same algorithm we will see. But the thing is that I've lost something. What I've lost ends up giving me things that were not true in my database, but now are true. Okay? So the lossless decomposition has to do with not losing correspondences between attributes, right? So this is not lossless because there is at least one instance. For that instance, I will get different results when I decompose and join back. There may be many instances where this is not true, but what we care is there should be no such instances. Okay? So this is what the algorithm is going to test. So this is called Chase algorithm. Okay? And it actually tests for, it chases functional dependencies. Now for this algorithm, I don't care about the projection of functional dependencies. All I care is the original set, right? So for example, I had A, B, and C, and I had a, okay, let's try to add one more attribute here. And suppose I have A and B implies D, and C and D implies A. Okay. I need to change this to C implies A. Okay, so now let's say that I will decompose this as A, B, and C, and this as B, C, and D. Okay. So Let's check to see if this is true. What I can do is I'm going to create a new relation. I'm actually going to create a relation with tuples for the original relation R. Okay? So this is called a canonical database. And so the idea is that basically I'm going to check if, let's say I took this relation and then stored it in two separate relations, R1 and R2. So if I didn't have R before, in R1 I can find A, B, and C. I can find that this A, this B, and this C are related. Okay? So anytime I have knowns and unknowns, knowns will have no subscript, unknowns are going to have a subscript. So if I look at a tuple in R1, A, B, and C are known, but what is unknown is D. So for anything that is unknown, I'm going to give it a subscript. So let's call this D1. And for R2, I'm going to do the same, but for R2, when I look at the tuple, B, C, and D are known, but A is unknown, right? So I'm going to put another one. And generally, the convention is the first row is ones, the second row is twos, so that you're always going to get a different one, okay? So looking at a tuple in R1, I have A, B, and C, but D is not known. Looking at a tuple in R2, I have B, C, and D, but A is unknown. The question is, can I recover from these two the unknown values? Can I find A2 or D1 from any of these relations? The only way I can do that is by looking at the original functional dependencies. So remember, they say that, for example, this one says if you have two tuples with the same A and B, then the D values should be the same. So I can check to see if they have the same A and B. Okay? That's not the case. The other one says if you have the same C values, then you can recover the A value, right? So I have actually two tuples with the same C value, right? So what I can do is I can go and find a tuple with the same C value from the two relations. Then I can take this known value and I can copy it here. So I can replace this one with A. Okay. So at any point, if you have recovered all the missing values for one of these, then that means this is a lossless decomposition. That there is no value with no subscript is left, then this is a lossless decomposition. Okay. So in fact, that's exactly what I did for this one, because I actually constructed the same thing here, right? I had two relations. For R1, A and C are known, but B1 is not known. And for R2, B and C are known, but A2 is not known. I have a functional dependency that says A implies B. So if I find two tuples with the same A value, I can copy the B values. But there is no two tuples with the same A value, right? So as a result, this is where I stop. And the nice thing is that if you actually fail, so you apply all functional dependencies, but you cannot find a tuple that has no subscript, this is actually an example instance that will actually be lost, exactly like I did. So this is how you actually generate a counterexample, right? So you write the algorithm, you apply rules until you find a tuple with no subscript. If there is such a tuple, you know it's lossless. If there is no such tuple, then the resulting relation is actually a counterexample of an instance. When you decompose and join, you will not get the same result. Okay, so this is the idea of a chase algorithm. Okay, so the algorithm is formally defined on course notes, but let's try to do a little bit more exciting example. I spent a lot of time writing this, so hope somebody reads it. You should really actually read the book. The book is better than me, but we are going to try to do this example right now. Okay. So the nice thing about the Chase algorithm is that it works for any decomposition, not just two, but any number of decomposed relations. So let's write this down and try to solve this one together so that we can see the mechanics a bit better. So I have A, B, C, D, E, and F. I have B implies E, E and F implies C, B, C implies A, and A and D implies E. I really don't care if this is in minimal cover because implication is an implication. So this will work regardless of whether this is in minimal cover or not. So I have A, B, C, and F. R2 is A, D, and E. And R3 is B, D, and F. Okay. So my relation has 6 attributes. After I decompose, they are distributed to all these 3 relations. So if I join them back, am I guaranteed to recover the original relation? So, in other words, let's construct this canonical database of A, B, C, D, E, and F. Okay. So, for example, in R1, A, B, C, and F are known. So, A, B, C, and F. So that means D is unknown and E is unknown. I'm going to use a subscript for that. For R2, I have A, D, and E. So A, D, and E are known. The rest are unknown. So I'm going to use subscripts. And for R3, B, D, and F are known. B, D, and F. So this is unknown, this is unknown, this is unknown. Okay? Making sure that I get different unknowns, I keep using a different subscript, right? Because this unknown is different than this unknown. Now I'm going to use my functional dependencies to see what I can recover. Okay? So for example, is there a case that I have the same B values? They can be B's or they can be, the same subscript, as long as it's the same value. Right? Doesn't have to be just known. As long as it is the same value, it's fine. So, do I? Right, so I have the same B values. That means these two E values can be the same. Right now they are unknowns, right? So they will continue to be unknown, but they can be the same unknown. So you can make them E1 or you can make them both E3. That's fine. So I'm going to make both of them E1. Okay. All right, and I use E and F implies C. So I have the same E and the same F. So that means these two C's can be the same. So now I have a known and an unknown. In this case, my preference is to make sure that I copy the known, right? So this I'm going to make into C. So let's write down where we are. I have A, B, C, D1, E1, F. I have A, B2, C2, D, E, and F, 2. And I have A3, B, C, D, E1, and F. Okay. I still don't have one row that has no subscripts, so I don't know for sure. And you have to do this until you no longer can apply any more rules, right? So can I apply the C implies A? First and third again, so I have B and C, B and C. So they already have the same F. Did I copy that wrong? All right, so that, BC implies A. So the same BC, so they have A and A3, so I'm going to change this to an A, right? So I can copy the known. Any more? right? So I have a, not that one, this AD, and this AD implies E, so I can copy this E, right? So now this row has no subscripts, right? So in fact, following the chain of functional dependencies, if they were true before in my original relation, which is the whole point of functional dependencies, then they will be true after I finish, and this is lossless, yes. You will go through each functional dependency once. No, you can go as many times as you want. Right. So, I mean, I do stop as soon as I find one example. Yes. So the way that I think about this is that when you do joins, right, you're trying to match matching things, right? But the things that you are matching basically are you're matching that. So let's go back to this example here. So like this example, right? So when you join here, right, you're actually matching on the attribute C, right? Because this and this are matching because they have the same C, right? But because when you match because of that, right, which is like what we are doing with the join, right? You find the same two C's, right? But when you find the same two C's, right, that means that you need to be finding a correspondence between A and B. But there is nothing that C implies, right? So like, let's say we do a simpler example here. Right, so let's say okay, so you have A and B, but no C, right? And here you have A and C, but no B, right? So when you do a join between these two, you will be doing with respect to A, right? Which is the common attribute, right? And the nice thing is that A is actually implies the other attribute, which is B, right? So when you do a join, the values that you get from R1 are actually going to be values that depend on the thing that you are joining, right? So because of that, I will actually put a B value here that is supposed to be there. Whereas in the other one, when I joined on C, but the values that I got had nothing to do with what was in it because there was no functional dependency on C, right? So the idea is that, the join is actually bringing values that should be there, not extra values, right? So the chase algorithm looks at basically, multiple functional dependencies, but ultimately what you want is one of these relations to have a primary key that's also a primary key for the original one, roughly, okay? So, but, that's kind of a little wishy-washy. Especially it doesn't work when you have many, right? Think about that. When you do a join, the values that you bring in should be valid values. And that's because of the functional dependency. Does that make sense? Right? So because when you do a join on A, you bring the good B values, then you actually are recovering the relation. You're not bringing unknown values. That's what it's trying to accomplish. Okay? I hope that was clear. Yes?
So we joined on A, and then the bottom row has no more subscripts, so that's just proving that R, A, B, and C.
This is a lossless decomposition, right? So here,
if we went through all this functional dependencies, if you go through it again,
you can do as many times as you want, as long as you apply them correctly. If you end up with a table here that has a row that has no subscripts, then it is lossless.
Would you ever go through all those that would come through?
Yep, that was the example here, right? So if you apply this one, right, this is what you start with, and you can't really change this anymore, right? So when you end up with a table that still has subscripts and you cannot change it anymore, this is actually an instance for which this will be lossy, right? You can show that if I took this, decomposed, and took the join, I will not get the same relation. So not only it is guaranteed that if you find one is lossless, if you don't, then this is a counterexample. Questions? Okay. All right. So let's go back to the beginning. Okay. So we said that this was not a good data model because, in fact, you repeated lots of information multiple times for things that were not related to it. And, you know, I will make a Marco Rubio joke, but I will not. So the idea here is that since this is not actually in BCNF, that is the main cause of that. So what we would like to do is to actually make it into BCNF. So if I have a relation that is not in BCNF, okay, so if R is not in BCNF, then what we are going to do is we are going to pick a functional dependency that violates it because it doesn't have a super key on the left, right? So find a FD x y in minimal basis f that violates BCNF. So let's give a very simple example, exactly what I just had. So you have A implies B. The key is AC. It is not in BCNF because this one functional dependency violates it. Then I'm going to do it as follows. I'm going to create a decomposition that has everything in this functional dependency. So create R1 containing attributes X union Y. So I'm going to create one functional dependency that has A and B. Okay. Take everything that A implies, put it in one functional, one relation. Okay. Then create the remaining relation. So R2 will have all attributes of X of R except Y. So the remaining relation is going to be R2. That's going to have everything except for B. So it's going to have A and C. Now you can find the projection of functional dependencies to these. So A implies B, and this is nothing. Okay, so these are projections. And now check, is R1 in Boyce Codd normal form? Is R1 in Boyce Codd? Yes. Is R2 in Boyce Codd? Yes, no functional dependencies, nothing to violate. If they are both in Boyce Codd, you can stop. If they are not in Boyce Codd, then now you have to continue recursively. Okay, let's do one more. So I have R A, B, C, and D. This is really a horrible data model. I don't know what you were thinking, but we'll do that. Okay? Something like this. So the key for this is A, right? So key is A. That means both of these violate Boy's code normal form. So I can decompose using any one of them. There's one that is better than the other one, but this is for you to decide. There is no algorithm that tells you one is better, okay? You have to eyeball and see. So I'm going to use C implies D. So I'm going to have R1, C implies D. So this will be C implies D. And R2 is going to be everything except for D. So it's going to be A, B, and C. So if you do the projection, you will find, okay. So for R1, key is C. This is in B, C, and F. So that means R1 is good. I'm done with R1. For R2, key is A. So this still violates B, C, and F. B implies C is not in B, C, and F. So I have to decompose R2 again. So I'm going to decompose this into let's call this R21 BC that has B implies C. And R22 is going to be A implies B, which actually has this one. This is in BCNF, this is in BCNF, so now I'm done. So in fact, my decompositions are AB, BC, and CD. Okay. Now the problem with Boy's code normal form decomposition is that it is not guaranteed to always give you the same results. So if I did this in a different order, I will get slightly different ones, okay? Bear with me for one more second, then I will stop. Okay, so I had the same, like this, but suppose I decided to use B implies C. So I will actually get R1, A, B, R1 will be B and C, and R2 will be A, B, and D. So I will actually get A implies B, B implies C here, and here I will get A implies B, and A implies D. Is that correct? And I also have B implies D. So I don't need this one. Okay. So this is still not in Boy's code normal form because of this one. So I will get A implies B and B and D. Okay. So I ended up getting AB, BC, and BD. Is this the same as the one I had before? I got two different examples, right? So depending on which order you apply, you may get totally different ones. And in fact, what you can prove to yourself is that this one is functional dependency preserving while this one is not. Okay? So this is the problem with Boy's code normal form. So what I want you to do is take the two relations that we had and decompose them to Boy's code. So when we come on Thursday, we will do this quickly. And then we will do third normal form. and then we will move on to ER modeling. But we will talk about the pros and cons of each one so that we can fully understand.